So there we go. So we're going to be going over graph traversals, MSTs, and shortest paths today. It'll be somewhat of an extension from yesterday, but we're going to go more in depth into certain trickier traversals, I guess. So, okay, so for today, we're going to go over kind of like an intro on basic definitions of trees and graphs. Then we'll go into like the traversals themselves, DAGs, minimum spanning trees, and shortest path algorithms like dijkstras and A star. So for the basics, we did go over two different things in 61B. We went over trees, which are structures that follow a few basic rules. So some of them are, if there are n nodes, there are n minus 1 edges, as seen here. There is exactly one path from every node to every other node, assuming that the tree is undirected. And the above two rules means that trees are fully connected and contain no cycles. And the parent node points toward its child, and the root of the tree is a node with no parent nodes, and the leaf has no child nodes, as seen here. So graphs are basically like trees, but they're a bit more generic. So graphs allow cycles, and simple graphs don't allow parallel edges, which means two or more edges connecting to the same exact two nodes, or self edges, where a vertex can have an edge right back to itself, which sounds a bit confusing, but don't worry, because it doesn't exist in graphs. And graphs may be directed or undirected. Okay, so now we can go over two kind of bigger concepts that we learned, DFS and BFS. Now, DFS is the simpler one, and this will be a bit more easy to understand. So, of course, you can do DFS and BFS both on trees and graphs. And trees are something that are a bit more easily doable, but I do know that at least when I did this like course, I found the version on graphs to be a bit more like difficult. So I'll go over that for today. So DFS is usually done with a stack, and depth first search exists because you're literally seeing how deep you can go. And for example, we can go through this one here, and here we can pick any arbitrary node at first. I'm going to pick 0 because it's just standing out there very obviously. And instead of going from 0 to 3,
What? They dropped a new Squiddy.
then I can go immediately from 0 to 1 to 2 to 5 to 6, and then I would traverse to 3, and then I would go down from there, because in general, instead of going wide as possible, you want to travel against an edge as deep as possible. So instead of going 0, 1 and then 0, 3, then I'd go all the way down. And the pseudocode would kind of make it make more sense. So here we can see that this would be S, and this would be the one that we visited already. So if S is the target T, then you can return true, which means you've gotten to the end already. But for the child and unmarked neighbors, that is, if a neighbor is marked, and then you would be ignoring it because you don't want to go to a node that you've already gone to, especially if it's like all the way down here. There's no reason to come back to number 6. So I'd have to go all the way back to 0 and then move forward again, if that's clear. But if there's any questions, like keep putting it in the chat, and like I can answer it if there's some issues. But for BFS, it's a little bit more complex. It's not the same thing as just going down. This is more, rather than depth, it's the complete opposite. It's breadth first search. So this is usually done using a queue. So BFS is usually standing for breadth first search, and it's also analogous to level order. So this means you're going to search wide and not deep. And you're going to be visiting nodes based off of their distance to the source or starting point. For graphs, we're going to visit all of our immediate children before continuing on to our grandchildren. And that means you're going to visit all nodes 1 edges from our source, which means there's 1 edge from 0 to 1. but there's 2 edges from 0 to 1 to 2, because this would be like my root source. And whatever distance that I take from there onward would count as the number of edges. So this is the kind of tool that I use to keep track of it. And like, this is something that's very common. But the queue, as you can see, is empty now because we haven't really started going through this problem yet. But this is a good way to keep track of things. So you can start off by saying F as in like false, I haven't visited them yet. And then slowly, as you start visiting things, you can start putting in T's for these instead. And the edge 2 would be basically where you came from before. And then the distance 2 would be the like distance you are from the original source. So this will make a little more sense once I go into the pseudocode. So first we should initialize the fringe, and a fringe is basically a term that we just use for data structures where we're using to store the nodes on the frontier of our traversal's discovery process. And the next nodes it's willing to look at, for that BFS, we would use a queue for our fringe. And edge 2, just to give basic definitions, is a map that helps us track how we got to a certain node. And then we're going to get to that node N by following along the edge V. And dist 2 is a map that helps us track how far we are from vertex. So assuming that each edge is worth a distance of 1, then the distance to N is just 1 more than the distance to get to V. So this is something that's explained a little more in the pseudocode, but I think it would be really helpful if we went through this example. So as you can see, this is completed here, which just makes it easier when you go back and refer to these slides. But I think we can just go over this as a quick demo. So here we're going to start off with our 0, and we don't have an edge 2 because for the number 0, the distance to that number is 0. So this is what we're starting with, as we saw in the previous slide. But then after that, I'm going to go in breadthwise and go into my number 1. So the edge 2 for number 1 came from 0, and there's a distance of 1. And then now I'm going to expand it from how can I go into, now that I only have 1 distance space from 0 to 1 from my source, now I can go 2 times as much. So I'll see, okay, if I traverse 2 edges, then where do I land? Well, one place is 2, and that's 2 places from the source, which is seen here. For the number 2, it comes from the number 1, and the distance from the source is 2. And you can say the same for number 4. Hence, it has the same exact values as you saw for number 2. And then like so, you would keep traversing farther and farther. So whenever you have equal distances, you would kind of move by distance. So like as your distance increases, I wouldn't do 1, 0, 1, 4, 3, etc. I would instead move like level by level. So I would go distance 2, then I would go for 2 to 4. And then for distance is 3, then I would go to the number 3. And I would also go to the number 5. Because once I get to number 4, this is just one other edge away. So that's 3 spaces from the source, if that makes sense. But yeah, that is kind of a recap of BFS, and I think we can move on for now. Okay, now we can go on to DAGs. Oh yeah, but as Anjali said, like it's like a bit different. Like when you have stacks and queues, like we discussed in class, it's the things where you're thinking about like popping off versus just pushing them in. But yeah, I think we can move on to DAGs because it just gets a bit more complex from here.
All right, before we do move on to DAGs, if anybody has any questions that they would like to ask, you can either write it in the chat right now for any DFS, BFS graphs questions, or you can, unmute your mic and ask it out loud. All right. It looks like we don't. Oh, okay. We have one question. Why can't they go to 5 from 2 instead of 4? Trinity, do you want to answer this question or? Well, I
Yeah.
can answer it really quickly
Okay.
too. But basically, so when we go, this is BFS, correct? Yeah. So when we go from go to 5, it's actually, you know, a tie. So the kind of distance from whether you go from, you know, 4 to 5 or 2 to 5, they both have, you know, the same, you know, same level, same depth. So it's actually arbitrary whether you go from 5 from to 5 from 2 or from 4. So you can do either one. It's handled kind of arbitrarily. In this case, we showed an example going from 4.
Like sometimes in exams, this examples was with just numbers, but yeah, like Anjali's saying in the chat, like in an exam situation, maybe it's alphabetical order if it's just letters, and then you would, you know, be able to tie break using that. But Caitlin, yeah, you're right. Like in this case, you can use either or because they are the same distance from each other.
All right, I'm gonna share my screen. All right. Okay, so we're gonna be going over DAGs. So first of all, you know, what are DAGs? DAGs are known also as directed acyclic graphs. And as its name might suggest, DAGs have two properties. They're graphs that are directed, so it's going to be a directed graph, and it's going to be acyclic, meaning that there's going to be no cycles present within that graph. To our right, I kind of give us an example of what a DAG might look like. And you know, some examples of DAGs that you may have already seen is trees. So trees are a type or a subcategory of a directed acyclic graph. And also, you know, you may see like course prerequisites. Those can also be represented as, you know, directed acyclic graphs. So I know we just got into starting talking about DAGs, but let's see, you know, with the definitions that we've provided, which ones do you guys think, you guys can write it in the chat, are directed acyclic graphs? Okay. All right, let's go over them now. So if you said A, yes, A is a directed acyclic graph. You can see, although, you know, there may look like there's a cycle present here, but because this graph is directed, you can actually notice if you follow these edges that you can't, you know, go around in a cycle for any of these nodes. And it's directed. Next, we'll go to B. B is not it's not a directed acyclic graph. It's actually a directed cyclic graph. You can see that there's a cycle present from B to C, C to E, E to D, D to B. And because there is a cycle present within this directed graph, it's not going to be a DAG. And finally, we have C, which is a undirected acyclic graph. Although we don't have a cycle, we can see that this graph is not directed, so it would not be a DAG. So good job, everybody. It seems everybody who wrote in the chat got it right. A is the only directed acyclic graph. Okay. Next, we're going to be going on to MSTs. MSTs are also known as minimum spanning trees. they're basically a subset of edges within a undirected weighted graph. And those edges connect all the vertices within the graph using the lowest total cost of edges. So we can see within, our example to our right, we have a graph with vertices A, B, C, and D, and we're connecting these vertices using the edges 1, 3, and 3, which gives us a total weight of 7. And there would be no other way to connect all these vertices together without using, at least in this graph, these particular edges. All right. And also keep in mind that a minimum spanning tree is a tree, so we will not have any cycles. Okay. So before we move on, is there any questions on MST or DAGs? Yeah, so directed basically means it has a direction within our edges. So we can see that, within our MST graph, it's undirected. So this edge between vertex A and D, it doesn't suggest that we have to go in a particular direction. We can either go from A to D or D to A. But for our directed acyclic graphs, we can see we have an edge denoted with an arrow, meaning that we can go from vertex A to B, but we cannot go from vertex B to A because it is directed from A to B. All right. Next, we're going to be looking at what is known as the cut property. So first of all, what is a cut? A cut is an assignment of nodes or vertices within a graph into two non-empty sets. This basically is a fancy way of saying I'm going to take, some vertices of my graph and split it into two different categories. So in our example to our right, we see that we have, with this whole entire graph, we have these vertices over here within our S set grouped together. And then we have another group of vertices within this set here. So we've split this graph into two different sets. So this would be a cut. A crossing edge is the edges that connect one set of a cut to another. So because edge E and edge E prime are connecting these two sets from the cut, these would be our crossing edges. So then, now that we know the definition of cut and crossing edge, what is the cut property? The cut property denotes that the minimum weight of a crossing edge will always be in a MST. And a slight correction here, it's not the MST. We can have multiple MSTs within a graph. So a minimum weight crossing edge will be present within a MST.
To clarify on Jessie's question in the chat where she asked, so each cut would already be an MST of itself before we even have the cut property. I just want to say not necessarily. So the idea behind the cut property is that you take half of the vertices and put them in one side, or not necessarily half, any split, and the other portion and put it on the other side. And then you examine all of the lines that go between those two halves. and you know that the vertex of the lowest weight that goes between these two halves is for sure in the MST. We have this example already has the two halves as MSTs as well, but all that really matters is that there's two disjoint sets of vertices, and you know that the lowest weight line that goes between them is definitely in the total MST.
Yeah.
So the cut property is independent of whether each half is in the MST or not, or each half already is sorted into the MST.
Yeah. And, kind of adding on to what Anjali said, regardless of whether, each subset or each set of our cut is an MST or not, we know that in an MST, we have to, connect all the vertices together. So it doesn't necessarily matter, what form these vertices are in, on the right-hand side or the left-hand side here, because we know that we're going to always have an edge that connects these two sets together. So because we need to have an edge within our crossing edges in the MST, the cut property will still apply, regardless of whether, each set is an MS already has already been, constructed as an MST or not. Right. So again, with crossing edges being the same weight, as long as it doesn't create a cycle, then equal or same weights of kind of minimum crossing edges are going to be handled arbitrarily. So again, another small quiz. We have a cut of vertices A, D, and B, C. Can you guys tell me what the crossing edges are for this given cut? All right, yeah, so it's going to be the edges from A to B, B to D, and D to C. These are because these are the edges connecting the two sets from our cut together. And the edge that will be contained within the MST is going to be DC. And we can see that, in fact, the cut property holds as the smallest or the minimum crossing edge, which is 3, is contained within this graph's MST. Okay, so next we're going to use an algorithm called Prim's algorithm, which helps us find the MST within a graph. Prim's algorithm relies on the cut property that we just saw beforehand, but we go step by step to provide a clear visualization of how Prim's algorithm actually works. So first, what we're going to do is we're going to split the vertices into 2 sections. And for our case, we'll have it as, for Prim's algorithm, it will be, the vertices that have been added to the MST, and then the vertices that have not been added to the MST yet. So at first, we begin with MST. So there's no vertices that have been added to the MST. And there have been, A, B, C, D, E are not added to the MST yet. Okay, so we'll first randomly pick a starting vertex to run our Prim's algorithm on. So we're going to add that vertex to our MST. And now what we have is we have 2 sets, one having the vertex A within the vertexes that have been processed into our MST. And then we have the rest of our vertices, B, C, D, and E, that have not been visited yet. So from here, we can see that now we have two non-empty sets. And if you guys remember from the cut property, this means that the crossing edges between these two sets, the minimum crossing edge will be contained within our MST. So if we look at the three edges that we have between our set that our MST set and our not visited set, we can see that the edges are 8, 7, and 3. So which edge would be contained in our MST in this case? Yeah, so AB will be the edge contained within our MST. That's because out of the three edges that we have, 8, 7, and 3, 3 is our minimum crossing edge. So what we're going to do is we're going to add 3 into our MST. Because 3 connects vertices A and B, we add B into our MST that we were creating so far. And now we have non-visited set CDE and our MST set AB. This table that I created below is just to kind of give our MST. We can see that we start with vertex A, and then we have the edge B connected to A, representing this edge that we created. Okay. Okay, moving on. Now we have MST set AB right over here. And our non-visited set is going to include C, D, and E. So the crossing edges for these two sets are going to be 8, 7, 4, and 1. So which edge would we want to add in our MST here? Yeah, exactly. So we want to add BC to our MST. And once we do so, we move our vertex C into our MST set. And now we only have 2 vertices left in our not visited set. So we repeat this process again. Now we have vertices A, B, C, and set with vertices D and E. We have our crossing edges here. And which edge would we want to add here? So we have AE, AD, BD, or CD. Yeah, we would want to add CD because CD has the lowest weighted edge. So I'm going to add the edge CD. Now we have only, one edge remaining, which is, or one vertex remaining that we have to include in our MST. And we do the same process again. Now we have vertices A, B, C, D within our MST set, and E within this set of vertices that we have not visited yet. And the edges connecting those two sets are 8 and 3. So for our final edge, which edge would we want to utilize? All right, so it's either going to be DE or AE. And because we want to be choosing the minimum crossing edge, we're going to be adding DE to our MST. And once our not visited set is empty, then we've visited all the edges within our Prim's algorithm. This will then, in result, give us our MST. you can see that A to B, B to C, C to D, D to E gives us our MST. Are there any questions on Prim's algorithm? So there's a question about distance too. So I really like the intuition that's going on here. So Prim's algorithm is actually very similar to Dijkstra's algorithm, which is what we're going to look at later on within our slides, when we keep track of the edges. But we do not actually have to keep track of distance 2 within our table because we're only considering the edges and the crossing edges in order to select which edge is in our MST. Any more questions on Prim's algorithm? Okay, so we're going to be moving on to then the runtime of Prim's algorithm. As we mentioned a little bit before, the algorithm of Prim's algorithm is very similar to Dijkstra's. We'll review it a little bit later, but essentially Prim's algorithm is going to have the same runtime as Dijkstra's. And when we use a binary heap, we're going to get the runtime of O of E log V. And I believe later on in the slides, we'll be exploring the runtime of Dijkstra's, and you'll hopefully gain a better understanding of why our Prim's algorithm has this particular runtime. Yeah, so a binary heap is basically, we've seen heaps in our, in our sorting algorithms and just within our data structure section. A binary heap is just a heap that only can have 2 children.
To clarify on Justin's questions, I feel like people who are watching on YouTube might have the same question. The lines around V and E are not referring to absolute value. They're referring to the cardinality of a set, which is the number of items in the set. So V and E is actually the set of vertices and the set of edges, and the lines are referring to the size of that set.
Yeah, so these V and E, the lines refer to cardinality, which basically means how many items are within this set, or the magnitude or size. Yeah, so we can use a Fibonacci heap. Patrick said, the fastest implementation of Dijkstra's uses something called Fibonacci heap. It's not in scope, but if you are interested, you can look it up in your own time to see kind of how the Fibonacci heap makes Dijkstra's fast, or Prim's and Dijkstra's faster. Okay, next we're going to be looking at Kruskal's algorithm. So Kruskal's algorithm is also another algorithm used to find MSTs. So we're just going to go through, similar as Prim's, we're going to go through a visualization of Kruskal's, and then we'll look at its runtime. And for Jesse's question, do we implement Prim's algorithm using heaps? Yes. So we will be using, more often than not within the exams, because Fibonacci heap is out of our scope, we will assume that we are using binary heaps as the implementation for Prim's algorithm. Okay, moving on to Kruskal's algorithm. So first, we're going to have two sets, one with the edges that are going to be contained within our MST, and then edges that, that we have within our graph that we have not added to our MST yet. So when we run Kruskal's, first, what we're going to do is we're going to take our list of edges, and this is just an arbitrary ordering of our edges right now. I just picked 3, 8, 7, 3. I just made a random list of these edges, and then we're going to order them by their lengths. So now we can see that we have a list of our edges that are ordered from 1 through 8, going from least to greatest. Next, we're going to iterate through the edges within our ordered list and then try to add them into our MST set. So first, we're going to look at, the first element within our ordered list, which is 1. You can see that the edge between B and C, which is 1, and we can add this edge into our MST. Next, we're going to go to our next element, which is 2. We can add our element, which is 2, into our MST, so we just add it into our set of MST edges. We look at 3. I just picked arbitrary 3 because our edges are tied for A, B, and D, E. Again, if we want you guys to use some sort of tie-breaking scheme, we'll mention it explicitly on the exam. But we can see that with our edge of 3, I just picked A, B, and that can be added into our MST. Next, I'm going to add the next 3, which is the edge from D to E, which we can add. And then now we come to the case of 4. And we want to ask ourselves, can we add 4 to our MST? So can somebody tell me, what they think? Do you think we can add 4 to our MST? Yes or no? Yeah, exactly. So the general consensus is that we cannot add 4 or the edge BD to our MST because it creates a cycle. And that's absolutely correct. So beforehand, I was just adding our edges saying, oh, we can add 1, we can add 2, we can add 3, we can add 3. But every single time we add an edge, we want to check if it creates a cycle. Because if we create a cycle with our MST, then it's no longer a tree. So because when we try to add B and the edge between B and D, and it creates a cycle, we will not be adding the edge 4 into our MST. All right. So now we'll look at the edge AD, which is of length 7. Can we add AD to our MST? Yeah, and for the same reason as we can't add, this edge BD to our MST, we also can't add the edge AD to our MST because it creates a cycle. And lastly, we go to edges AE. And we notice that AE also creates a cycle. So because we iterated through our whole entire list of edges, then we realize that we've already have our MST. So yes, we can stop when all the nodes are connected. It really depends on your implementation of Kruskal's. So if you realize that if you have another check for, oh, have I, visited all my vertices, or until, we have our tracking of vertices has, been completely fulfilled, yes, you can stop Kruskal's algorithm early. And for do we use is connected to check whether, we have cycles? And yes, you do use the function is connected to check whether we have cycles within our MST. And we'll look at that a little bit later on. Okay. So for the runtime of Kruskals, and I'll get to some of the other questions a little bit later. We're going to be first sorting the edges. So there's E edges within the edges list, and sorting E edges takes on average E log E work. And within our actual Kruskal's algorithm, we're going to be iterating through E edges of our ordered list. And to check whether there's a cycle, we use the union find data structure. And we can have a log E runtime in order to add and check is connected to see whether we have cycles within our Kruskal's algorithm. And because we have an E log E runtime for sorting the edges, plus, sorry, this should be E log E. This should be E log E right over here as well. Because we have an E log E plus E log E runtime, we can see that it's O of E log E, which is also equal to O of E log V. Okay, so let me look at some of the questions. Will prims always yield the same MST as Kruskals? No, not always, but they're both going to give us a valid MST. V in this case is going to be vertices. So there's another question. How do we know E log E is equal to E log V? Yeah, so we know, that, this runtime is O of E log E. Log E can also be written as log V because we know that essentially for E is going to be at most V squared. So we can replace E log E with E log V squared. And then log V squared is also 2 log V. And then we take out the constant of 2, giving us E log V. Yeah. Does the runtime analysis rely on E greater than V?
So this does, okay, so this is kind of a fun question. Does this runtime analysis rely on E greater than V? In a sense, it does, because if you think about it, of a graph in which there are less edges than vertices, other than, the n-1, is an unconnected graph, which obviously not all the nodes are reachable from all other nodes. So then that kind of messes with this. So in general, yes, kind of, but not like for any other reason, I believe. Because if you think about it, right, like edges by default, by in a connected graph, that there necessarily must be almost as many edges as vertices, or like up to way more. So we just kind of assume that the number of edges is usually greater than the number of vertices. But it doesn't like rely on it. It still works if it's like a tree and there's one less edge than vertice. It just, doesn't really mean anything because then all the edges are in the MST.
Yeah, exactly. So if we ever have a case in which E is less than V, it's going to be that, the graph has or is a tree in essence. There's
Or
only going to be
unconnected.
one edge. Well, yeah. So yeah, they're all going to be connected through one edge. So you're going to have to use every single edge to connect all the vertices.
Cham, do you want to ask your question?
Yeah, can you go over once more why the edge check cycle is log E?
The edge check cycle? Oh, I see. So here I would recommend looking at the union find data structure. I don't think we have enough time to go over exactly how the union find data structure works. But if you look at, kind of slides through which we explain the union find data structure, we can notice that basically with the union find data structure, we can add edges and kind of we can run is connected to check whether two vertices are connected so far. And if we want to add an edge between two vertices that are already connected, then we find out that there's a cycle. And this takes log E.
The easier way to think of this might be in the E log V situation. So obviously to check for you to iterate through all the edges. And then if you recall from like weighted quick union and all that, it takes log of however many log n time to check is connected when you have like a weighted quick union, right? It just so happens that log V is equal to log E. And the reason for this is that the largest number of edges you can have in a simple graph is E squared, right? So V equals at most E equals at most V squared. So when we have log V, we can plug in E squared into that, which gives you log of E squared. But if you remember our log rules from when we covered asymptotics, log of E squared can be rewritten as 2 times log of E. And obviously, when it comes to asymptotics, we get rid of coefficients. So it might be easier to conceptualize it in the E log V scenario, but that also means that E log E is also true necessarily. Does that make sense to everybody?
Is it because the union quick union is like based off of a tree?
Yeah, like if you remember weighted quick unions, right? If you're fuzzy on this, by the way, we covered this yesterday in our review session, and there's also like more materials on this that you can go over because we don't have time to cover it today. But weighted quick unions, they deal with like sets that you're checking whether or not items are in the same set or not. And that's basically the same thing we're doing here. We're checking to see whether all the vertices are in the same set. And so it's the same idea.
Okay,
but we're going to move on. If you're still confused about this, I highly recommend you check out the weighted quick union lecture and the discussion for that and all that.
Yeah, as Anjali said, if you're having trouble understanding for checking for cycles using the union find data structure, we covered it in yesterday's exam review session for data structures. And moving on, we have shortest path algorithms, which will be covered by Nandini. Nandini, I think you're muted. Yeah.
Oh yeah, I'm going to share my screen real quick. Okay, can everyone see my screen? Yes.
Yep, you're good to go.
Okay. Also, if anyone has any questions throughout, I'll also be asking some questions to you guys. I'd really prefer if instead of using the chat, you unmuted yourself and asked your questions or answered my questions, just because it's a little hard to like manage the chat at the same time. Okay, so we're going to be going over shortest path algorithms. So there are two main ones that we learned in 61B, and that's dijkstras and A star. So the first one that we're going to go over is dijkstras. So the purpose of dijkstras is to find the shortest path from a node, which we call the source node, to all other nodes in the graph. And this ends up producing a shortest path tree, where even if you want to find the shortest path between two nodes and those nodes aren't the source nodes, that would still be the shortest path between those nodes just because of the way dijkstras is organized. And so the method behind dijkstras is the first thing that we do is we add the first node, our source node, to a priority queue, which we're going to call our fringe. And the priority for each node is given by the total weight to the node from the source. And higher priority is lower weight. So it's not that like the higher the priority, the higher the weight. The higher the priority, the lower the weight. And the weight for the source node is 0, and all other nodes start with infinity. The second step is to pop the node with the smallest weight, update the children weights if needed. Well, they're not children's, they're more neighbors. Update neighbor weights if needed and add them to the fringe. And then you repeat steps 2 and 3 until all the nodes are removed, and you'll end up with your shortest path tree. So in this particular example for dijkstras, I'm starting with an empty fringe that I've just added a source node in. However, in code and like implementing it yourself, you'll see in the A* example, I started the fringe out with
Nandini, sorry, I think you are sharing perhaps the wrong screen or the wrong window, because all we see is the shortest path algorithms slide on like Google Chrome.
Okay, wait, it says it's paused. Okay, now can you see it?
Yep.
Okay, sorry, I already said all of this. You guys can go back to the slides and see it. Okay, can you guys see that? Yeah.
Yeah, you're all good.
Okay, cool. So this is the dijkstras algorithm that we're going to be going over. Our source node is 0. And so in our fringe, we've just put in 0 and we've put in the weight as 0. And we're also maintaining 2 lists, distance 2 and edge 2. And in code, how you want to maintain these lists is really up to you, whether you want to use an array or anything like that. It's totally up to you. But since we're doing this manually, I just have them as like this kind of table. So the first thing that we're going to do is we're going to look at our fringe. We're going to pop the node with the smallest weight. And in that case, that's 0. And what we're going to do after that is we're going to add its neighbors into our fringe and update our distance 2 and edge 2 lists. And so the 2 neighbors for 0 are 1 and 7. And the distance to 1 from 0 is 4. And the distance from 7 to 7 from 0 is 8. And so we're just going to update those. And notice the edge 2 is 0 because the edge 2 right before 4 and 7 is 0. The next thing we're going to do is we're going to pop 1 because 1 is our smallest weight currently in our fringe. And once we pop 1, we're going to have to update its neighbors. So 1 has 2 neighbors, 7 and 2. And neither 7 nor 2 have been fully visited. And so we have to consider what is the weight, how much does it cost us to get to 7 through 1 versus how much does it cost to get to 7 through 0. So to get to 7 through 1, it costs us 4 plus 11, 15. And that is greater than what it costs to get to 7 from 0. So we're not going to update 7 at all. For 2, however, since 2 has not been touched at all, we're still at infinity. And so for 2, we can automatically put in the new weight, which is 12, because 0 to 1 is 4, and then 1 to 2 is 2, or 1 to 2 is 8. So 4 plus 8 is 12, and we can update that. But 7 will remain the same. And so now we have 1. 1's been popped, and so it's been visited. The way that I'm treating visited nodes is in the fringe, if they're crossed out, that means they've been visited. Additionally, I will be maintaining the shortest path tree using the highlights. Does anyone want to unmute themselves and say which node will be popped off next and how to update its neighbors? It's the one with the shortest or the smallest weight, if that helps. Okay, I'll give you guys this one, but next time let's try to get a little bit of participation just because it makes it a lot more fun. Sorry, what?
I can try answering that one.
Oh yeah, for sure.
100%, but because I'm not sure of the tie breaking technique, maybe it could be either the node 2 or 7, and then depending on, you can pick either one, or if there's like, you should prioritize the number. I would assume it would be node 2 to go to next, and then you would update the edges to 8 plus 4. which is
Okay,
right.
I'm going to stop you real quick. So
No,
why
you're
do
good.
you think that it's 2?
Because okay. Because it would be the shortest in comparison to the length to go to 7 or 2. It's between 7 or 2. I don't.
Okay, I understand where you're like coming from, because you're saying to get to 7 through 1, right?
Mm-hmm.
So actually right now, since we didn't update 7, right? Because we noticed that to go to 7 through 1, it would cost us more than going to 7 just from 0. So we didn't update that. And so technically right now, we're still going to 7 through 0. So the cost to get to 7 is still 8 right now. So knowing that information, would
okay.
you change your answer?
Yes. So I would probably just go directly to 7 then, ignoring, like, we didn't have to use 0 to 1, that edge.
Exactly. Yeah.
Thank you.
And then after so let's say we pop 7. So now 7 has some neighbors. What would we update in the neighbors?
In the neighbors, meaning the table to the right.
Yeah, so 7 is, you notice how 7's connected to 1, 8, and 6. However, 1's already been fully visited, so we don't really need to do anything with 1. But how would we update the distance to and edge to for 8 and 6?
8 would be 15, and then 6 would be 7 or 9.
Exactly. And their edge to would be 7, because for now we've popped 7, and we're saying theoretically, if the shortest path to get to 8 and 6 is through 7, we're just going to put that in our table preemptively. We're saying that, okay, for now we think that this is our shortest path. We might have to update that later on, but for now we're saying that is our shortest path. And so we're going to update our table with those distances going through 7, and our edge to would be 7. Does that make sense?
Yeah, thank you.
Of course, you did great. So now we're going to pop 7, just like Hillary said. And now we have updated, we've added in 8 and 6. So 8 with the cost of 15, right? Because to get to 8 through 7, it costs 15. And then for 6, it's a cost of 9. So now after this, does anyone want to unmute themselves and say what our next step would be?
You would pop 6 and update 5.
So we'd pop 6 because 6 has the lowest weight. And why did you choose to update 5 and not 8?
Going from either 7 or 6 to get to 8, use the same weights, but you penalize a greater number of edges.
Yeah, so in this particular case, they are the same weights, and we haven't specified any tie breaking scheme. In this case, we're leaving the edge with the less, or we're leaving the node with the least edges in, like Bryant said. But typically in an exam situation, or even when you're trying to implement this in code, you would have to specify some kind of tie breaking technique. So yeah, like Bryant said, we popped 6. And we have updated 5. 5 is 8 plus 1 plus 2, which is 11. So now what would be the next node that we pop?
You would pop 5 because it's the shortest distance away.
And which nodes would we update? What are 5's neighbors?
5's neighbors are 2, 3, and 4. So you're gonna generate those fringes since you now know the distances of those. And
so,
yeah, those neighbors.
Yeah, so for 2, for example, right? So 2 is already in our distance to and edge to. It's no longer infinity because we determined that to get to 2 through 1, it costs us 12. So to get to 2 through 5, how much would it cost us?
That would cost us 15. So we wouldn't update it then.
Exactly, yeah. So the only 2 that we're technically going to update are 3 and 4, because currently 3 and 4 are infinity, and anything less than infinity, we would need to update it with. So like Cedric said, we pop 5 and we update 3 and 4, which have weights of 25 and 21. And if you're confused about that, you can kind of just trace the path from 0 through 7, through 6, through 5, all the way to 3, and then all the way to 4. if you're confused as to how we got 25 and 21. Okay, so what would be the next node that we pop?
I think we would pop 2 next.
Yes, we would pop 2. And which nodes would we update after popping 2?
So the neighbors are 6, 5, 3, and 1, out of which 6 is out, 5 is out, 1 is out, so possibly 3. So yeah, 12 plus 7 is less than 25, so we would update 3.
So we would update 3. Also for 2, I think you just missed the 8 in the middle. So 2's neighbor is actually not 6, it's 8. So would we update 8?
We actually would update 8, yeah.
Yeah, and like you mentioned, 5 is out, and so we don't need to touch 5. 1 is out, 2, you get to 2 through 1. And so we're going to update both 8 and 3 because going through 2 would actually be faster for both of those. And so you can see we've made those changes in our distance to edge to list along with our fringe. So what would be the next one that we pop?
Would it be vertex 8?
Yeah, it'd be vertex 8. And are there any neighbors that we'd have to update in the case of 8?
No, because you already visited all of 8's neighbors.
Exactly. Yeah. So for 8, we can just pop that edge and establish that to get to 8, we would go through 2. And we already know that because of our distance to an edge to list. So now that we've popped 8, what would be our next node that we pop?
Hi, sorry, I have a quick question about how we changed or updated both vertex 3 and 8.
Yeah.
Can you re-explain why we had to do that?
Yeah, for sure.
Given that we find another shortest path.
Yeah, so on this slide, we determined that we were now going to pop 2 because 2 had the lowest weight. And so we were like, okay, it's time for 2 to go. And we noticed that 2 has the neighbors 8 and 3. And so now we need to see, okay, so we have a shortest path to get to 2. Is it possible that any of 2's neighbors would benefit going through 2 instead of the other path that they've been taking? And so in this case, we determined that to get to 8 through 2, it would be 4 plus 8 plus 2, which is 14, which right now 8 has a cost of 15, right? Because if we go from 0 to 7 to 6 to 8, it would be 15. So to go through 2, it would actually be faster for 8. And it's a very similar idea for 3. So for 3, to get to 3 from 7, 6, and 5, it would cost us 25, right? Because we have 8 plus 1 plus 2 plus 14. However, to get to 3 through 2, it would only cost us 19 because we have 4 plus 8 plus 7. And that's why we updated 8 and 3. Does that make sense?
Yes, thank you so much.
Yeah, of course. Does anyone else have any other questions? Feel free to unmute yourself. If not, does someone want to tell me which node we're going to pop now?
Yeah, I think here we're going to go pop 3.
Exactly. So we're going to pop 3. And the only neighbor left is 4. Would 4 be updated through 3?
No, I don't think so.
Why not?
So right now we have a distance of 19 to get to 3, but the path from 3 to 4 is like a distance of 9. 9 plus 19 is greater than 21.
Exactly, yeah. So we're just going to pop 3. We're not going to change anything else. And then our final one left to pop is 4. And we know that we popped 4 through 5. And so that's where that tree will take us. So does anyone have any questions about dijkstras in general or this particular example that they want to unmute themselves and ask?
Yeah, just to clarify, so you only highlight those that have the shortest path. If it's larger than, let's say, for example, that 19 plus 9, if it's too big, then we'll just not color it in and we'll focus on the previous path that was most efficient.
Yeah, so my highlighting is basically to illustrate that we're creating this idea of like a shortest path tree, but in reality, you can trace all the highlighting back to our distance to and edge to tables. So if you look at 4, the edge to for 4 is 5. And that's why I've made that link between 4 and 5 instead of between 3 and 4. And so the highlighting is really just there as a visual. So you can see like this idea of a shortest path tree. But in terms of like the edges and the distances, they're also in these lists, and you can trace back all the highlighting using the edge to list. Does that make sense?
Yeah, thank you.
Of course. So if anyone doesn't have any more questions, I'm going to move on to A star. So A star is super similar to dijkstras, except we have this idea of a heuristic function and heuristic values. Also, A star has a goal node, whereas for dijkstras, we didn't really have a goal node. We had a source node, and we were kind of like, okay, go crazy, make your shortest path tree however you want in whichever direction. However, for A star, we have this idea of a goal because we have this idea of a heuristic function, which is basically it estimates the cost to get from one node to the goal. And the reason we have that is because dijkstras, since it does end up spreading out over the entire graph because it tests every single potential shortest path, it costs a lot more than A star does. Whereas A star is a lot more efficient because it has this estimate. It's like, okay, if there's an estimate of 5, if I go through this node to get to the goal, and there's an estimate of 3, if I go through this other node to get to the goal, I'll probably want to go through the other node to get to the goal. Whereas dijkstras doesn't have that level of intuition because it doesn't have that idea of an estimate. However, in terms of implementing it, it's very similar to dijkstras with just a couple of tweaks here and there. So the purpose of the A star algorithm is to find the shortest path from point to point using a heuristic function, which prioritizes nodes that may yield a better path while dijkstras explores all paths, basically what I was saying. And as for the heuristic function, typically you're given the heuristic values. There's no such thing as like a heuristic function. There are different ways to calculate heuristics and stuff, but for our intents and purposes, heuristic values will be given to you. And if the heuristic values are all 0, then it becomes dijkstras because we're not given any estimate, we're not given any idea of a path that may be faster. And the lower the heuristic is, the more A star expands in its search, the higher it is, the more compact the search is. So we're going to go through an example. So here's an example. Our goal node is G and our start node is A. So this is the heuristic table that's usually given to you. And so we didn't do anything to find this table or these values, they were given to us. And this is a situation in which the fringe is already preemptively filled. Whereas in dijkstras, we were filling in the fringe as we were going along. In this case, the fringe is already filled with the infinity values. In terms of actual technicalities, it doesn't really make any difference. It's just up to you how you want to implement it. So the first thing that we're going to do is we're going to put in A with a distance of 0 because to get to A from A costs us nothing. And we are going to pop A and update its children. So our children in this case, or it's not children, it's neighbors. But the neighbors in this case are B and D. And so now to get to B from A, it costs us 1. However, we still have this idea of a heuristic value. So we actually have to incorporate that. And so the heuristic to get from B to G is 6. And so we're going to add that to our fringe along with the actual weight. Because the idea is, okay, you go to A through B, you know for a fact that to get from A through B, it costs you 1. However, you also want to say, okay, maybe like if I kind of want to guess how much more it'll take to get to G, that's when the heuristic value comes into play. So the heuristic is saying, maybe it'll cost us around 6 to get from B through G. And so for B in the priority queue, we're just going to do 1 plus 6. For D, similar thing, except it costs 2 to get from A through D. And D has a heuristic of 5. So we're going to add the 2, we're going to get 7. Now, since B and D both have the same weight, and I haven't mentioned any tie-breaking scheme, we're going to assume this tie-breaking scheme is random. However, typically, it's like numerical or alphabetical. But in this case, we're going to assume it's random. So we're going to pop B next, and we're going to update B's children. So in this case, B's neighbors. So B only has one neighbor, which is 6. And so what we do is we take the cost to get from A through C, so that's 1 plus 3, which is 4. And then we take the heuristic to get that, which is the estimate to get from C to G, which in this case is 2. So you do 1 plus 4 plus 2, and we get 6. So does anyone want to unmute themselves and say which neighbor or which node would be popped off next and how to update the neighbors?
You're going to want to pop off C,
Mhm.
and then you'd update all of C's neighbors by taking the distance to C from A, which is 4, and then adding the heuristic values.
So you're really, really close, except in this case. So for example, if we wanted to update F, we would take 4, but we would also add 2 because we're assuming that we've gotten to F, but then for F to G, we're going to add the heuristic value, which is 1. However, in the case of G, since G is our goal, we're just going to have 1 plus 3 plus 4, which is 8. So you're really close, except the heuristic value comes after we've already gotten to the neighbors. Does that make sense?
Yes, thank you.
So we pop 6.
Can you clarify there? Would it be 4 plus 2 equals 6, or would it be, where did you get the extra, like 1 plus 3 plus 4?
Oh, the 1 plus 3 plus 4 is if we're going from A to B to C to G, because C has 2 neighbors. In this case, it has F and G, right? So for F, it was 1 plus 3 plus 2 plus the heuristic, which if we look at our table is 1. Right? So it's 1 plus 3 plus 2 plus 1. But then we also have this other neighbor of C, which is G, and that would be 1 plus 3 plus 4. Does that make sense?
Oh, so we don't rely on the heuristic shown on the graph where it says from C to G, it's going to take 2.
Yeah, so the reason we don't, so for C to G, the reason we're not using the estimate anymore is because we're saying definitively that G is C's neighbor. G is C's neighbor, and now we're going through C to get to G. And so we have this defined weight between those two. We're no longer using the estimate. Does that make sense? Yeah.
Yes, that does. And so why does it have that number from C to G? It's 2 when in reality it's 4.
Yeah, so that's an estimate. It's usually an underestimate.
Oh,
So basically, for example, like in the previous slides, when we had B and its neighbor was C, we were like, we don't know anything about this middle portion with the arrows between F and G and C. For all we know, between C and G, there were like 3 other nodes. But all we know is that we have this estimate, and they're like, okay, maybe between C and G it would cost it 2, maybe. And that's why we use the idea of a heuristic when we don't definitively know how we're getting from C to G. However, once we've popped C, then we can see very clearly that G is one of C's neighbors. And so we don't have to depend on the heuristic anymore. Does that make sense?
Perfect. Yes, thank you so much.
Yeah, of course. Okay, so we have popped C and updated its neighbors. Yeah, okay. So now does anyone want to unmute themselves? I guess in this case, you can't really tell me which one to unpop or which one to pop because like I said, it's random. So in this case, I chose to pop F, which if you guys can see, F and D have the same weight. So it could have been F or D, but just because of how I chose to do the example, I'm choosing to pop F. So you pop F and F's only neighbor is G. And so this is another case in which we're dropping the heuristics completely because we see a clear path from F to G. And so we would update G. Would we update G? Yes, we would update G because to get to G through F, it's 1 plus 3 plus 2 plus 1, which is 7, which is less than what it takes to get to G for now. So we're just going to update G, pop F. Does anyone want to unmute themselves and say which one we're going to pop next? Hint, it's not G.
It'd just be between D and G, but you said not G. So D.
It's not G because G is our goal. And we haven't visited all of our nodes. And so we wouldn't pop our goal yet. But again, like the tie-breaking scheme was not clear in this case. In most cases, it will be clear. So now let's say we pop D. How would we update its neighbors? Noah, did you want to say how? Or if not, anyone else?
If you pop D, then hold on. You pop D, and then you would update E to be, I think, just maybe 10.
So I'm assuming you're looking at.
It would be 5.
Sorry, did you say a number?
5 for E.
So the way, okay, let's break down how we're looking at the heuristic, right? So we have A through D, that's confirmed, right? So that's 2. We also know D through E is confirmed because we have pop D and we see that E is its neighbor. So right now we have 5. However, we have no clue what happens between E and G. Again, like I said, like for all we know, there's 3 other nodes between E and G. So we have to depend on the heuristic. In this case, the heuristic happens to be the same as the weight between E and G, but in a lot of cases that won't be the case. So we're going to use a heuristic, which if we look at the table from E to G, in theory would cost 3. And so we do 3 plus 3 plus 2, which will give us 8. Does that make sense?
Yeah, sorry.
No, you're all good.
Thank
Okay,
you.
yeah. So now we've popped D, we've updated E. And since between E and G, G is our goal. And so we don't really want to pop our goal yet because we haven't visited everything. And so that leaves us with E to pop. And we would also want to check, is it faster to get to G through E, or is the current path that we have to get to G the fastest? So we can do a quick arithmetic check. So to get from A to D is 2, D to E is 3, E to G is 3, that will give us 8. And currently it costs us 7 to get to G through F. So we're not going to update G, we're just going to pop E. And at the very end, we're going to pop G and add that to our little shortest path tree. And yeah, and then we're done with our A-star algorithm. So I'll stop sharing my screen. Does anyone have any questions, any concerns? I can also pull up the slides again. Preeti, do you have a question?
Yeah, so is my understanding of like A-star correct in that like its purpose is so that we don't have to go over the entire tree, but rather that since we know the start and target node, we get to the target node faster, right? But in the case of like this example, there was node D and node F that both had like, I guess weights 8 on our fringe. And if we were to use an alphabetical tiebreaker to choose D instead, wouldn't that like defeat the purpose of using A-star over dijkstras?
Yeah, so this is also a relatively simpler graph. It's not necessarily faster, it's just more efficient in the sense that dijkstras, since it doesn't have this idea of an estimate, like if you're at a node, it has no clue how much it'll take to get to our goal. However, A-star has some kind of idea because of the heuristic, and so it just spreads out less. And you can't really see that when you're manually going through it, just because even in dijkstras, when we're manually going through it, we don't really check every possibility just because we're humans and we can have that intuition. We don't really need to see it. But in theory, the idea of like heuristics is that it would ideally check less paths than dijkstras. Does that make sense?
Right, so this was just like a special instance, but in an overall like average sense, we would get there faster.
We would typically, I'm not actually sure if we'll get there faster. I think Anjali,
you should get there faster in the sense that you would technically have to visit fewer edges and fewer nodes. I think the confusion here is because I'm sorry, I might have missed it. I believe we might have popped F before D, which I don't think we were supposed to do. I think we were supposed to pop D first, because I think the case here is that we're tie breaking alphabetically. And so when 2 edges have the same predicted distance basically to the goal node, then we pop the ones alphabetically first. And that, I think if you switch that in your mind, everything else will make sense and you'll get the same result. The idea behind A star is that you don't want to visit every node, especially in very large graphs, such as like Google Maps and stuff like that. And yeah, it should be faster almost all the time.
Okay, thank you. And like one last question. So if we get to G through F, for example, for whatever reason, like would we stop there or would we continue to check?
Yep. So the moment you get to the goal node, once you popped it out of the whatever it's called, the fringe, you are done. You shouldn't go anymore. And the reason for that is because just like dijkstras, once you visited a node, any path to that node can only be longer than the path you've already taken. Right. And this is important. This is why we have to have our heuristic be less than the true path to the node, less than or equal to. Because if the heuristic can be greater than the true path, then that breaks this relationship and we can no longer trust that once we've popped the node, that there is no better path. So because of this, the heuristic has to be less than or equal to the true distance from your current node to the goal node.
Right. Thank you so much.
Also, just to clarify, I know it seemed like we were popping it alphabetically. I was really just popping it randomly. Typically though, when you have like alphabetical nodes, you do pop it alphabetically, but that's why F was popped before D, just to clarify. Hillary, do you have a question?
Yeah, so we use the word terminology pop, and that's the same thing as like visiting, right?
Yeah, technically. So if in theory, typically when you implement these algorithms, you'd have some kind of like visited array or some way to keep track of all the nodes that you've already visited. So when you pop a node, you add it to your visited array. And that's why I did the little highlight between them because they've already been seen.
Thank you.
Jesse, you have a question?
Oh yeah, I'm just a little confused still about the fringe and A star. So on slide 67, you have E is 8 and G is 7 in the PQ fringe. And so I thought you would actually still go to G first because G has a higher priority of 7 rather than 8.
Oh, are you talking about when we popped E instead of A or E instead of G?
Yeah.
So typically G wouldn't really be in our fringe. I put G in there just to see, just to show.
I'm going to hop in here, and I think that was actually a mistake, and we should have popped G and never visited E at all. So I think this is a mistake, and we'll fix it in the slides before we release them after this review session. I apologize. We must have missed it earlier.
Wait, so just to clarify, would I still have G in the fringe then?
Yeah, so you would have G in the fringe as normal node. Once G has been popped and visited, the entire A star algorithm stops. It does not matter whether there are nodes still in the fringe because any path that goes through those nodes will inherently take a longer time than the path we've already found to our goal node.
Oh, okay, thank you.
Any other questions?
Wait, sorry, to clarify, so you're saying that we don't have to visit all nodes once we hit G, then we don't have to go through D or E?
Yeah, because G is our goal node.
Okay, then why did we check through A, D, and to E, that path?
That was a mistake on my part, but E should never have been visited. D would have been visited if we were tie breaking alphabetically. But in this case, D and E probably should never have been visited just because we had this path from A through B through C through F through G.
Oh, okay, but what guarantees that that's going to be the shortest path? Is it just because of the heuristic and stuff?
It's because of the heuristic and also the path to get from A through B through C, just because of the way the algorithm's structured that at the end, you will have like the shortest path because we've been finding the shortest paths throughout. Does that make sense?
Absolutely, thanks.
Any other questions from anyone?
Yeah, I also had a question. So shortest path tree is essentially the tree that traces all the shortest paths to each node, right? But in A star, you choose a specific vertex like G, to be the end goal. So I don't really know why we would do that, because aren't we trying to find the shortest path for each of the other nodes as well? Like say node B or C or F, etc.
Yeah, so typically the shortest path tree is only a result of Dijkstra's algorithm, because in Dijkstra's algorithm, we actually go through and visit every node. And that's what makes A star more efficient than Dijkstra's algorithm, just because we have this idea that we're going to go to every single node and we're not stopping until all the nodes are gone, versus A star where we stop just when we hit the goal. And so A star will give us the shortest path from the source to the goal, but it won't necessarily give the shortest path with all the nodes, because not all the nodes may have been visited. Does that make sense?
Oh yeah, but for Dijkstra, you'd still get the shortest path to every node.
Yes. So for example, if we wanted to get to 6 from 0, this would be the shortest way to get to 6.
To add a little bit of context for that, the reason we would want A star when we could use dijkstras, because theoretically, you know, dijkstras just can give you the shortest path to anywhere, is like, imagine you're in San Francisco and you want to plan a road trip to New York, right? And so you have the map of the US, and you can think of roads as the edges between cities. And there are so many cities in the US, way too many cities for you to run a shortest paths algorithm that goes from San Francisco to every possible city. But with this kind of map view, you can kind of get an estimate for how long each road is. I mean, sure, some roads might be going over mountains and valleys and might actually take longer than you think, but that bird's eye view gives you a kind of reasonable heuristic for how long each road will be. So we run A star instead of dijkstras because we only really care about the final path from San Francisco to New York. We don't really care about the path from San Francisco to every city in the US.
Yeah, okay, thank you.
Does anyone have any other questions to me, David, or Trinity? If not, Anjali, should we stop the recording or?
Yeah, quickly though, does anyone else have any other questions that they're willing to ask before we end the recording? Again, it's great if you guys ask questions now, just so that's included in the recording. Austin, go ahead.
Yeah, it's a quick question. Could we discuss the runtimes for A star and dijkstras?
Yeah, sure. So the runtimes for A star and dijkstras are again dependent on the number of nodes you pull out. So the ultimate runtime for both dijkstras and A star are the same when you in big O notation, because in worst case for A star, you're basically running dijkstras, right? You have a bad heuristic, or not a bad heuristic, but just a useless heuristic, and you end up having to run dijkstras anyway. And so in that situation, both of them will have the same big O runtime, which I believe off the top of my head is V log V, very similar to the runtime for, I believe, what we said for MSTs.
Yeah.
And it's for the same.
Yeah, it would be V plus E times log V.
Yeah. And it's
So
for a
V
very similar
plus
reason.
E in quotations times log V, which gives us E log V, V log V, I think.
Yeah, it's V plus E times log V. And the reason is just because of you have this visiting everything takes that long with the priority queue sorting and stuff like that. So if you want more information on that runtime, I think we discuss it quite a bit on a lecture, which might be a better place to get that, because I don't think we have a slide on it. It's kind of hard to explain runtime over Zoom without slides.
Thank you.
Is it possible that given a bad heuristic that A star will have a worse runtime than dijkstras? So if you mean by a bad heuristic that it's admissible but useless, then no, right? Because in dijkstras, you visit every node through every possible edge, essentially, right? You make sure you keep checking, you're like, how is this possibly a better path? No, then we won't. So dijkstras is a worst case where we visit every edge. If you have an inadmissible heuristic, it is possible for your A star to return the wrong answer, which I think there's an example of that in lecture. And in that case, the runtime will still be better than dijkstras. It'll just return the wrong answer. Hillary?
Yeah, two questions. One, what does inadmissible mean? I searched it up and I still don't understand in context of this code. And then the second question is that I can ask after you answer this first one.
Yeah. So inadmissible is just what we say when we mean a heuristic that that causes A star to return the wrong answer. So like I said earlier, we want A star to always have a heuristic that is actually less or equal to the real path from point A to point B. And the reason is because if we have a heuristic that's greater than that path, it's possible for A star to overlook it and be like, well, that path is going to take too long. We shouldn't even try it when that is secretly the shortest path. So our heuristic always has to be less than the actual correct path. And so those heuristics, we call them admissible because they make A star work. And then we call heuristics that don't work inadmissible.
Gotcha.
Yeah.
Thank you. And that brings me to my second question about the path. I know you used the example of San Francisco, but when we look at the path to A, D, and E, we don't have to visit those nodes precisely, but we are able to still predict the shortest path to A, D, and E still, given that there's only one connecting line. But if there was a bridging factor between vertex B and D, sorry, this is kind of like a visual looking back at the slides. If there was a bridge between those that caused a longer path, would that be a problem in terms of finding the shortest path to D?
In terms of finding the shortest path to D, so I'm assuming you're saying there's like an edge of, let's say, length 3 or something, right? So in that case, it shouldn't be the problem. Again, if we have an admissible heuristic, it'll run at worst like dijkstras. And if you remember, dijkstras will return the shortest path. It might peer at it. It might like look at it and be like, is this possibly a better path? But ultimately, so the heuristic will always be, well, it'll have to be admissible. That means that it won't cause an issue ultimately is what I'm trying to say. It shouldn't cause an issue if it's admissible. Yeah, it's kind of hard to explain this without having it kind of drawn out, but yeah, if that examples, yeah, I think the examples in lecture are quite good for this. And it might be more helpful to look through those.
Yeah, no worries. Thank you, Anjali. That was great.
Yeah, if you guys have any questions on more like individual stuff that we covered here, this was meant more as like a survey of like, here's all the graph stuff we covered. If you're weak in any of these areas, you might want to take a look at the materials we have. So I encourage you to post on Ed and ask questions or go back into like lecture and discussion that covered this more in depth, just because we only have a little bit of time and we're covering like 2 months worth of lecture right now. So yeah, any other kind of questions that you guys want me to answer real quick? Okay. So, yeah, I think we can stop the recording now in that case.